All right, welcome back, everybody. Math 35, day 23. We are doing 14.1 on polynomial functions today. And we're going to start 14.2. I don't think we're going to finish it. This is on rational and irrational roots or solutions. Let's say roots of polynomial functions. For those of you that are interested in a Math 54 class on the Tulare campus in fall, all the trig classes have filled up, and I've gotten a trig class to open up here in the fall, and no one else wanted to teach it, so I get to teach it. It's not on the class search yet, but you guys are going to be the first to know. It's on Monday, Wednesday from 8:10 to 10 or 10 o'clock. So it's early in the morning, Monday and Wednesday, not Monday through Wednesday, but Monday, Wednesday. In this room, starting in fall. I don't know that they have the CRN number for it yet. It doesn't even show up on the class search yet. It'll be Math 54. If you're looking for a trig class or the pre-calc B class, or the next class in sequence, I'm teaching in fall out here. If you're having a hard time getting into one, or you want to be on Tulare, or even better yet, you want me in particular, you can have me for Math 154.
Are you going to also do online classes with that, or only?
It is just face-to-face.
Okay.
However, Jackie, if you enroll, I am going to record everything. The only thing that you really would need to worry about is showing up on test days.
Okay.
I don't want to announce that to everybody though.
Thank you.
Because otherwise I end up with an MPS class again. Before people even enroll. You're better, people tend to do better when you're here. So it's not there yet, but it will be. I don't know the CRN number. It'll be Monday and Wednesday, 8:10 to 10. So back to this. So what's a polynomial function? A polynomial function looks like something like this. We have f of x equals a n x to the n plus a n minus 1 x to the n minus 1. And we get down to a1 x to the 1 plus a0 x to the 0, or just plus a0, because x to the 0 equals 1. The exponents are non-negative integers. You do not want fractions, you do not want negatives. And I would even say positive, but we have the x to the 0, and 0 is a positive. A sub n is real, all of them are real numbers. So that's a polynomial function. Then you will hear me say something like root of a polynomial. A root of a polynomial is, a root is a solution to f of x equals 0. Where we take this whole thing and set it equal to 0. We tend to use the word solution is for any equation. Any equation. F of x, whatever that is, equal to 0. Root is used for root or 0. They call them the zeros. Roots or zeros are for polynomials only. So like f of x equals 1/5 x to the 5th minus pi times x to the 4th plus x squared minus 1.7x plus 2 is a polynomial. We're not going to work with anything like that because that's a shitty polynomial. But the important thing to know is exponents are positive. Positive integers, the ones you see. And the coefficients are real. Negative pi is a real number. It is not a pretty number. In fact, just making a negative is just turns my stomach a little bit when we talk about pi. So if I were to line up this up here, I could say a sub 5 equals 1/5. A sub 4 equals negative pi. A sub 3, there is no x cubed. So that's like having a 0x cubed. A sub 2 is 1 because there's no coefficient listed. A sub 1 is negative 1.7. And a sub 0 is 2. This a sub I business, is whatever the subscript is, isn't really important. I just wanted you to understand, like, why do we have these subscripts? And the reason why we have these subscripts is, like, from the quadratic formula, or from quadratic formula, we're used to doing shit like this. So in the quadratic formula, a goes with x squared, b or c. But if I were to go x cubed, now a is for different terms. And that sucks. So we use the a with the subscript. I'm going to say I as a subscript. And those are consistent no matter how I write it. The a with the subscript isn't so important as long as you recognize the subscript matches the exponent for the variable. If you go into trigonometry, if you go into calculus and on, this is consistent from here on. You will see this all the time. In fact, calculus subscripts show up a lot.
Kind of like the difference quotient. So those are calculus.
Kind of like the difference quotient shows up in calculus. What we're learning here is tools for math for the real world. Calculus solves stuff like engineering problems and stuff like that. Solves economic problems, it solves all sorts of things. So. I tried my key on my door today, it didn't work, and I'm like, I just got here and I don't have time to go over and like get the battery changed. I made sure it was my key, not just the door, her key worked. And she said she'd take it over for me and get my battery replaced while I was teaching. She's a very wonderful lady.
So what would, so like you were saying, there's this other form which is ax squared plus bx plus c. Where there are different variables, but we're listing the A format that's just to describe the exponent that's there.
The A, like in our current format. The one we're doing now, this would be A3 x cubed plus A2 x squared. Plus A1 x plus A0 equals 0. So the subscript matches the exponent.
The exponent. That translates to meaning something else later.
Not that it means something else, it's just we use this notation a lot later. All right, so. Quick question for you. Does x equal 1 solve? G of x equals x cubed minus 3x squared. Plus x plus 1.
I think so, yes.
Why?
Because it's going in the orders that we're currently going in, like the subscripts and the
Is there a way I could find out?
Plug it in.
Plug it in.
Just plug it in. Let's not guess. Just plug it in. It equals 0 and 0 means. This is g of x equals 0. G of 1 equals 0. It is a root. It is a solution. It solves x cubed minus 3x squared plus x plus 1 equals 0. What? You guys say something with calculus or derivative? Covered it. No. All right, everyone get that? Does -1? I just want to make sure everybody's on the same page.
no, it doesn't solve.
No, it doesn't. If I stick in -1, what do I get?
You get a positive 3 instead of a negative 3, so it'd be 3 plus 3 is 6.
How did you get positive?
Oh, just kidding.
It should be -1, -3, -1, and +1 is -4. Is that what you guys, anybody else getting that? I'm doing that in my head, so I might have,
Yeah, I think that's a.
so not a solution. Or root. All right, next thing we need to know here is the remainder theorem. Nope, we're not doing that yet. Repeated roots. Let's talk about repeated roots first. if I have x plus 1 squared times x minus 2 equals 0. This is x plus 1 times x plus 1 times x minus 2 equals 0. And the roots or zeros are set each one of these. If I set each of these equal to 0, I can find the zeros or the solutions of this. And I get x equals -1, x equals -1, or x equals 2.
You should, if we're looking for roots for 4, -1 twice.
Yes, it's going to be very important for what we're doing to the rest of chapter 14.
Yeah.
In fact, it drastically changes the way the graph looks. So what we say here is -1 is a root with multiplicity. That's a great word. Multiplicity of 2. So multiplicity is how often does a root repeat? I'm going to give you a quick little sketch of this function right here. Real quick. Oh, maybe I should have done this. I got -1 and I got 2. And I don't know where it happens, but I know it crosses here. It comes up and hits, goes back up, hits -1, bounces off -1, and does this. So we're gonna, when we do like 14.3 or 4, we're gonna see things with multiplicity of 1 cross the graph. Things of even multiplicity bounce off the x-axis. And things of odd multiplicity kind of do a little wiggle across it, you'll see. Like x cubed. You guys know what x cubed looks like? You get does some shit like that. So like this crosses in a straight line, but this comes in at one way, kind of does a little twist and crosses a different way. Okay. And this is x equals 0 multiplicity 3. If f of x equals x cubed. Because I could literally write that's x times x times x equals 0. X equals 0 or x equals 0 or x equals 0. So this is where we're going with it. This is why we care about repeated roots. And why we want to track them if the answer shows up more than once.
So if it was x to the 5th, it was all of the answers were x plus 1. It was 5x plus 1.
It would cross the x-axis 5 times. That's where we're going with it. Notice x squared. What does x squared do? Bounces off the x-axis. So this has x equals 0 multiplicity of 2. We're doing graphing next week. But I just wanted to show you why we care. So there's like the motivation to keep track of this. Which one is? All right, so If I have f of x equals 2/3 x plus 6 squared times x plus 7 to the 4th power. What are my roots / multiplicity? The roots are what?
The roots of -6, so. Let's see, 6.
Not quite. Each one does it separately. So how many times does -6 show up? Twice. Because there's 2 parentheses. If I take the square and make it parentheses, multiplicity of 2. -7 is multiplicity of 4. Because that is 2/3 x plus 6, x plus 6, x plus 7, x plus 7, x plus 7, x plus 7. And if I were to set it equal to 0, -6 shows up twice, -7 shows up 4 times. So if you've got it with it like written in x with exponents on the parentheses, it's really easy to see what the multiplicity is. It's the exponent.
So then it would not, -6 has its own multiplicity, -7 has its own multiplicity. And you record them separately.
Yes. Yes, definitely recorded separately. Ready for more? So we've got something called the remainder theorem. And it goes like this. The remainder of f of x divided by x minus r equals f of r. If you were here in the last hour, we took advantage of this property. We looked at it, we saw it in action. That's the remainder theorem. If I clear fractions, if I multiply through by x minus r, I could rewrite this as f of x equals x minus r times f of r. So if and only if f of r equals 0, then x minus r is a factor of f of x. And this is called the factor theorem. They're kind of related. And kind of like putting these two together, if it's a factor. Then x equals r is a root. Right, if we can factor it, set equal to 0, it's a root. And that means if I have x minus r, I can find, what does this mean? I can find roots. By plugging in values. And looking for. Like, let's say I plug in smiley face. Smiley face equals, I don't know, 7. If f of smiley face equals 0, then 7 is a root.
Meaning on the x-axis.
A root means it crosses the graph crosses out on the x-axis at that point. We'll go into that when we do the graphing thing, but it's good to see where we're going with it. That's why they call it a 0 of a polynomial. I don't know where they got the fucking root from. I really don't.
Yep.
I don't know why they chose the word root. I don't know how long it's been around in mathematical lingo. 0 makes sense because it's where y equals 0 on the graph. But they call them roots or zeros of a polynomial. And root is just syllables. So they tend to say that mathematicians are lazy butts. So let's take a look at one here. I've got x cubed plus x squared minus x plus 2 equals 0. Is -2 a root? So what we do is we just plug it in. Making sure to put the exponents outside of the parentheses so that we square or the exponent hits the negative sign.
Mr. Jones, I looked at one definition right now, if you look at the root word for the word root. It's a Latin word for, I think, RAD, like radix, and it means a starting point. So that can be why we use it.
Maybe. Huh. This is -8 plus 4 plus 2 plus 2 equals 0. That's a confirmed 0. So this means if f of x equals x cubed plus x squared minus x plus 2, I can write this as, this means x equals -2 as a root. If I add 2 to both sides, I see x plus 2 equals 0. I can write this as x plus 2 times some other function. Let's call it f2 rather than g. I can call it f2x. Right? If we can factor it, I should be able to have more parentheses here. And what's in here? So we did a lot of this in Math 335, the last class. A way of finding what's in here is called synthetic division. It's a fast form of doing polynomial division. If you want to see a lot of stuff done with it, watch the video after I upload it tonight. what we're gonna do is we take the root. And we put the coefficients. Go here. On the top row. And it looks kind of like an upside down division thing. The division bar. I'm gonna use the coefficients. I got a 1, I got a 1, I got a -1, and I got a 2. Make sure you guys get that set up and then we'll continue.
I'm confused. Where did the -2 come from?
Is -2 a root?
Oh, thank you.
Or if you know x plus 2 is a factor, setting this equal to 0 and solving. Same thing. So what we do, this just boils down to multiplication and addition. On the first number, you always bring the first number down. Then we're gonna take this -2, we're gonna multiply it by that number right there. And we're gonna add it up here. -2 times 1 is -2. And then I'm gonna add these two. 1 plus -2 is -1. And then I'm gonna do the multiplication again. -2 times -1 is +2. And I add. -1 plus 2 is +1. And I keep doing this. -2 times 1 is -2. I put that here. And I add and I get a 0. Now I'm gonna rewrite this without all the arrows showing what's going on. Because this is how you would normally see it when you do it. You're probably not gonna do the arrows. Other than the first arrow is always pretty handy. This bottom row is the coefficients in this case, f2 of x. A polynomial that is 1 degree lower. And I guess I should have said what degree means. I swear I've said degree before in the past, but if I haven't, the degree of a polynomial is the highest exponent. Largest exponent. So this was x cubed. I had f of x equal x cubed plus x squared minus x plus 2. And I have x plus 2 was my factor. Those are the coefficients of term 1 degree smaller. This is degree 3. So this is going to be degree 2 here. I'm going to have an x squared, an x, and a constant. And these numbers are the coefficients. So I'm gonna grab these and bring them down. 1, -1, +1. The 0 is the remainder. This turns out to be pretty helpful because synthetic division is the way we can keep breaking down these things into smaller and smaller terms until we get down to a quadratic. So like if we can keep finding roots. It does.
It does. What is it?
It's gotta be. It's one of two things. Shit, I'm making this difficult for you, aren't I?
Mm-hmm.
I really appreciate what you're doing for me. It's either that. Or.
Is that the wife?
Your phone.
It's Zoom.
Oh. All right, thank you.
Thank you. If we can keep finding roots, we can get down to a quadratic like we did here. And then use quadratic techniques to find the other two roots. Hey, Jackie, you know your volume is on, right?
Sorry.
It's okay. I was just letting you know. Before you say something you didn't want everybody to hear. So here, like, we're not gonna have very pretty roots, right? I don't even know if they're gonna be real.
I was gonna say, I feel like that's probably not real.
Well, we could do the quadratic formula. We've got 1 minus 4 times 1 times, where you're right, we're gonna have a -3 in the radical. We're not gonna have anything but complex roots after this. You'll learn about complex roots. Maybe in trig,
Let's say they graph, right, in some kind of way.
when you do the complex plane, they don't graph normally. So if we did that complex. If we did the quadratic formula here. I've got x squared minus x plus 1. This is -b is +1. Plus or minus the square root of -1 squared. Minus 4 times 1 times 1. All over 2 times 1.
Plus minus.
Plus or minus. It's -3, so I root 3 over 2.
Yeah.
So what this is gonna see when we see graphing this later on. We're gonna see that it crosses at -2, because that was one of our factors. It's gonna cross here. But it's not gonna cross again. So it's probably gonna do something like this.
Just like punching numbers.
Right,
Remember, we're just the other week there.
right. So there's a theorem, I think it's in the next section, actually. It's called, I don't know, the polynomial root theorem. Polynomial root theorem. A polynomial of degree n. Has at most n real roots. Like if it was shifted down, it could cross 3 times. But there's no way it's gonna cross 4. It could have 2, like we showed on the other one, where it bounced off. It only touched it twice.
Well, what about in this case, where our original problem had. It was a 3rd degree, but it was only crossed once.
That's why it says at most.
At most, most end.
And so it'll cross a maximum of n times. That might be an easier way of saying it. It will cross the x-axis a maximum of n times. But maybe less. Or can be less. Like it did here. I don't know where it goes back up. I don't know where it goes back down, but I'm pretty confident it does, as you'll see when we get to the next section. Not next section, but sometime this week. You guys ready to try one of these synthetic division things?
Yes.
I see a bunch of pins going, so you may be ready, but no one else is. I'm gonna slow my roll. Yeah, all the 54s are full. Holy shit.
Everything goes up super fast.
I know we're opening one out here, and I think they're gonna open one in Visalia. But I'm not sure about that one. I know this one's opening. But I just showed you the paperwork for it earlier. It's already gone through the process. Okay, let me give you guys one to try. We are gonna have f of x equals 2x cubed plus x squared minus 5x minus 3. And I can tell you that make sure I got that right coefficients here. 2, 1, -5, -3. X equals -3/2 is a root. Oh, thank you.
And it was the top one. On the email.
Oh, oh, I know what they needed for. It was for it. Yeah, David talk. Teacher talk. Get together in like a minute. Because this is just multiplication and addition. Shouldn't take you too long. It may just be multiplication, but it is a filthy fucking fraction, isn't it? So -3/2 times 2 is what? -3. Add those up, I get -2. -3/2 times -2 is what? +3. This is good. The fraction is going away, right? This is a good thing. I add those up, I got -2. We just saw what that is. This hasn't changed. That's a +3. So 0. So this is, I can write this if I do x equals -3/2 and I can add 3/2 to both sides and I get x plus 3/2. So this is x plus 3/2 times 2x squared minus 2x minus 2.
Which is another imaginary number answer.
It looks like it should be. Although that negative might change it. No, it's not gonna be imaginary. That negative's gonna change it. But notice if I factor out a 2 here, I can make this a little bit nicer, prettier looking. If I factor out a 2, this is x squared minus x minus 1. And I can multiply the 2 in here and I have 2x plus 3 times x squared minus x minus 1. Oh shit, that's deep. That's deep. And if I do the quadratic formula here, what do we get? I get 1 plus or minus square root of -1 squared minus 4 times 1 times -1 all over 2 times 1. So x equals 1 plus √5 plus or minus √5 over 2. Now, if I want to write it in factored form, and I'm going to. This is x equals 1 plus square root of 5 over 2. And x equals 1 minus square root of 5 over 2. So rather than like dealing with fractions, I'm just going to multiply through. And I will subtract -1 and negative square root of 5 from both sides. Just like I did up here where I moved it over. So if I wanted to write 2x cubed plus x squared minus 5x minus 3 in factored form, I have 2x plus 3. That 2 is really killing it. Maybe I shouldn't multiply through by 2. I'm not gonna multiply through by 2. I'm gonna put it back. X minus 1/2 minus square root of 5 over 2. And if I just subtract, I got x minus 1/2 plus square root of 5 over 2 right there. And the reason why I didn't like the 2x, because if this is a 2x and this is a 2x and this is a 2x, and I multiply all that shit together, I'm gonna have an 8x cubed. And I didn't start with an 8x cubed. This is actually something that shows up in the next section. I was probably gonna cover later. I thought I was gonna hit it on next Tuesday, but it actually reared its ugly head here. The conjugate root theorem. Showed up here. If x equals a plus bi is a root, then x equals a minus bi as a root. And that's really just stems from if x equals a plus like b root c is a root, then x equals a minus b root c is a root. When we were going over radicals, we talked about conjugates before. The conjugate, when you see a conjugate, it just means you have the same thing and something changes sign between them. A plus bi, a minus bi. A plus b root c, a minus b root c. We'll see that again later on. Let's take a 5-minute break. I realize we're digging into been in here for 55 minutes at least. Pause.
Yeah.
Right. That back then, parents unplugging your shit like you bitch. And they would get all mad, start yelling at your mother, calling her inappropriate names, disrespecting her just because. Yeah, teenagers are monsters.
Now go crazy with that.
Some do. Your mother didn't ever piss you off enough because you didn't have this save point problem.
No, I did in the old Ratchet Clay games, there was like. you had to get
Did
the-
your mom ever turn off your shit when you hadn't saved for like 3 hours?
Uh,
And you never got mad enough to yell at her?
Yeah,
She raised you to not disrespect her well then. You got some good whoopings for disrespecting mom at some point.
yeah.
Dad gave you a good whooping and you learned. Cause that shit don't come naturally. Y'all, nowadays kids don't know what the fuck I'm talking about. Some like beatings, you get in trouble for beating your child, but it's a hell of a way to learn to not do something.
Yeah. Well,
A good whooping will stop you from doing something you shouldn't do. And it's like helpful because it may be like something that'll get you killed when you're an adult.
Yeah.
But a good whooping as a child will make you like not, I don't know, jump off a tall building. I never jump off the roof. No, you're not. What? Okay, that's a bad idea.
But yeah, but then except you just find out, oh, okay, well, I'm just gonna go out of the house to do all that stuff. You know, I just gotta do that somebody else.
You gotta, yeah, like don't get caught, but still, the things
That's what happened.
your parents can discipline you for shit they don't know about.
See ya.
All right, let's kick this up a notch. The fuck? X to the 5th? X to the goddamn 5th? Why would you do this, Mr. Jones? I want to make sure that I have the right coefficients, so let me check this real quick. +7 plus 14. Because there's nothing like having shit that don't work. All right, so we want to find the other two roots.
And this wouldn't work unless we had those 3 roots, right?
Yeah,
We have to have those in order to.
these are going to give us a remainder of 0 when we do synthetic division. You could verify that these are roots by doing f of -2, f of 1, and f of 3/2, and these should all equal 0. As a reminder of how the remainder theorem plays in. But we're gonna do synthetic division. And I've got 2, -5, 7, 14, -54, and 36. What was handy about that last problem then? I had all odd numbers and that was what gave us doing the 3/2 was good. I don't want to do the 3/2 yet. Let's start with the 1. This is easy. This tells me my first step is I can have x equals 1 is the same as x minus 1 equals 0. My first factoring out of x minus 1 gives me 2x to the fourth minus 3x cubed plus 4x squared plus 18x minus 36. Now, if you had, like, I didn't have this in the way, I could literally write the next division thing right underneath it. But since I have my stuff in my way, I'm gonna rewrite that without that final 0. And do the next one. And I'm gonna go with -2. So x equals -2 is like x plus 2 equals 0. So this would be x minus 1. Oops. X plus 2. And then down to 2x cubed minus 7x squared plus 18x minus 18. And if I want to go smaller, I'm gonna have to deal with that shitty 3/2. I know. Oh. We have times -4 is -6. Eighteen minus 6 is 12. This actually works here. 3 times 6 is 18 and 0, and we don't have any. So the 3/2 wasn't that too bad at this point. So now we're down to the factored. This was x equals 3/2, so x minus 3/2. 2x squared minus 4x plus 12. I can factor a 2 out of that last one and move it into the parentheses before it. Take the 2 and put it over here. I have 2x minus 3 here. This will be x squared minus 2x plus 6. And now this is shitty because that doesn't factor, does it? So -b plus or minus b squared minus 4 times 1 times 6. It's gonna be complex. All over 2 times 1. This is 4 minus 24 on the inside, which is -20, which is -4 times 5 is 2i root 5 over 2, or 1 plus or minus I root 5. So my final factored form x minus 1 minus I root 5, x minus 1 plus I root 5. And you'll see that if you separate and move everything to the left. You'll get these last two.
Didn't do that other one. We'll let it out.
You got it?
That was wrong. Yeah, I was like, it does balance out. True.
Dare you question the great and powerful Oz? So you might be wondering, how the fuck did we come up with -2, 1, and 3/2 as roots?
Yes.
That seems like, that's like
How to find out.
pretty fucking lucky, right? No, it's not luck. There's a rhyme and a reason to this shit. And I'm not gonna start with a problem like this, because this one's got a lot of shit going on, but I'm gonna show you how it works. Is everyone good with what's on this page right now? Alright. So I'm gonna put in 2 videos. I will hit stop record. And start record again.